So for number 2 on the conservation of energy and work exam, we're going to take a look at this graph. So this is a force versus distance graph. And we have a 4.8 kilogram object that's initially moving with a velocity v0. We don't know what that is, along a frictionless track. And at the end of the track, it runs into a massless spring, causing the spring to compress. You start by doing a fancy experiment where you get the data pictured in the graph to the right by setting weights on top of the spring. You set up a ruler such that 0 is when the spring is not compressed at all, and the measurements are the distances that the spring is compressed. The graph shows the magnitude of the force exerted on the object by the spring as a function of the object's distance as the spring is compressed. Your lab partner was really annoying and told you that the slope of this graph is 456, but they didn't bother to label the x-axis of the graph. What is the spring constant of this spring? All right, so the reason why I put this next part on there is if you have no idea how to solve the problem, to write the answer of 235, that is because you need the spring constant to do parts B and C of this question. And I wanted to make sure that my students were able to solve those sections, even if they had no idea how to do part A. So one thing that you need to know is when you are doing force versus distance, you're going to have something times this distance in meters. And in fact, this is in reference to Hooke's law, F equals kx. So that distance is how far that the spring is compressed. And then that means that your k is your slope. Because if you think of this as y equals mx plus b, b is 0. So this is 0. This is on your x-axis. So your x is your distance here. And then y is your force, and that's on the y-axis. So that means that our slope is k. So if my really annoying lab partner gave me a slope of 456, that means that the spring constant is 456. And I do have units on my horizontal and vertical axes. I just don't have numbers. So I know that this is going to be newtons per meter. All right. So at this point on the test, if you used 456, or if you use 235, you will have gotten the correct answers for the rest of it. So either way, I will give you full credit. I'm going to show you how to do it with 456. All right, so second, you run the experiment with the object running into the spring as pictured below. The spring was originally a length of 0.19 meters and is compressed to a length of 0.07 meters before the 0.13 kilogram object is launched from rest. So you calculate the change in spring potential energy when you compress the spring. So if it was originally 0.19, so this is 0.19. And then when it's not moving, this distance here is 0.07. And then we're going to launch this thing. So it was 0.19, and then I squish it, I put the block against it, I let go, and my 0.13 kilogram is launched. So the change in spring potential energy, I'm going to just look at my change in energy. So at this point, my spring potential energy is 0. And at this point, I can calculate it using my spring potential energy equation. So spring potential energy is 1/2 times k times x squared. My k value was 456. And then for x, I need to find how much the spring was compressed. So it's not going to be 0.19, it's not going to be 0.07, it's going to be the difference between the two, because that's the change in length of my spring from it being in equilibrium or not compressed at all to the point that it's compressed. And then don't forget to square it. That's one of the common mistakes. So I'm going to go ahead and type this into a calculator. Alrighty, so now I have how much spring potential energy there is when it is compressed. And so now I'm going to go ahead and do part C. It asks me to calculate the speed of the object when the spring is at a length of 0.13 meters, which is this middle picture here. Now, the trick for this, first of all, is I'm going to go ahead and draw what the bar graph is going to look like in terms of energy at that point. And I'm going to go from when the spring is compressed to when the length is 0.13, so partially compressed. So at the beginning, I have all spring potential energy. My kinetic energy is going to be 0 because it's not moving at that point when the spring is compressed. And then at this middle point, I'm going to have both some spring potential energy and some kinetic energy. All right, so I'm going to go ahead and plug these things in. The nice thing is at the beginning, I already have how much spring potential energy there was because we just figured that out. So I'm going to plug that in here. So this is the 3.2832. And yes, I'm going to keep all of the numbers for the moment because I want to make sure that I keep things as precise as possible. And then the spring potential energy, when it's partially compressed, this is 1/2 times K. My K was 456. And then for this part here, I need to do how much my spring is no longer compressed. So and what's weird here is that I inadvertently made the new length 0.13 and the mass 0.13, so don't get confused. All right, so I'm going from a length of 0.07 to 0.13, so I need to find the change in length, so 0.13 minus 0.07, and then square that. And then I'm going to add to it my kinetic energy. So kinetic energy is 1/2 times my mass times velocity squared. My mass is also 0.13. And then the velocity is what I'm trying to find at that point. So I'm going to do a little bit of math here. All right, so I went ahead and plugged in those numbers, and then I subtracted 0.8208 from both sides. At this point, I need to then go ahead and divide by 0.065 and then solve. So I get 37.883 is equal to my velocity squared. And then to find that, I just need to square root it. And I get 6.15 meters per second is the velocity of the block at 0.13 meters. All right. And last but not least, we have part D. Oops, I just realized I was labeling these wrong. So for part D, I need to calculate the velocity of the object when the spring is no longer compressed at all. So that top picture. So again, I'm going to do an energy bar chart, but the difference here is that at the end, I have all kinetic energy. All right, so I went ahead and plugged in the numbers and went ahead and put those into my calculator as well. So I had a spring constant of 456. This is the change of length of the spring from not stretched at all to all the way compressed. And then we have the 1/2 mv squared, where this is the mass. And I'm solving for my velocity. So I went ahead and did that, plugged it in. Now I just need to divide by 0.065 on both sides. And I get 50.51 is equal to v squared. And then square root both sides to get rid of the square. And I get 7.107 meters per second. And that'll be my maximum velocity right when the spring is launching that block. If you have any questions, let me know. about number 2.